there's some people who believe that Python is simply a scripting language. There's a few people who firmly believe that it's something used by systems administrators, a few other people who believe that it's used simply by people playing with embedded devices. And then there's a few people who think that Python is a very large snake that is going to turn around and bite them. So upon my first week at Argonne, I was summoned into the office of quite possibly our most senior performance engineer, and he turns to me with a great big smile on his face, and then it starts to fade, and he goes, "People are doing high-performance computing with Python. How do we stop them?"
Does that person have a Russian accent?
Yes, that person has a very strong Russian accent. I managed to convince him that it was more or less like Fortran 77 and that, you just need to start everything in the right column. So this, of course, started a minor discussion internally about why Python, but first, what's Python? And so Python in HPC actually isn't really a new thing. If you turn back the Wayback Machine to 1989, Guido van Rossum was a staff member at the CWI in the Netherlands. He was working for the gentleman who kicked off the Minix operating system, Andrew Tenenbaum, who famously would go on to have a flame war with Linus Torvalds about Minix. And what he was looking to do was to provide a scripting language for a distributed operating system called the Amoeba operating system that ran across Sun workstations. And Guido had looked at Modula 3. They had an existing scripting language called ABC. But Guido's truest, deepest love was actually for Algol and Modula. But he wanted to write something actually that would appeal to Unix and C geeks. And so he started to sit down and crank out what would be the first version of Python, which came to a 1.0 version by, I want to say it was December of 1990. And then from there, it got pushed out onto Usenet, which is long gone, and everything kind of took off from there. The one big piece to remember is Guido was trying to specify a language. And so most of the places you go, the question is Python installed? And what people are actually saying is CPython, Guido's reference implementation, installed? There's actually a whole fleet of alternative interpreters out there. There's Jython, there's BytePython, there's IronPython for those of you who really like Windows HPC edition. There is the famous PyPy, which is Python with a JIT backend, and we'll kind of touch on why that's important in a little bit. There's even an alleged super secret Google build of Python that compiles. But right now in the modern era, because I still think of the world as before Python and after Python, so in this modern era, we have two major versions of the language that you tend to find in wide circulation, Python 2 and Python 3. To kind of give a couple notes about what the real split is after Python reached about version 2.4, Guido had kept taking all these notes about things he did wrong. And you have to understand that in the Python community, Guido van Rossum holds the title Benevolent Dictator for Life. That is to say, what Guido wants and what Guido thinks will eventually be the answer. He can be dissuaded. He cannot be dissuaded by much. So as he had been taking these notes about all these things he had done wrong or things that fell out that he felt made the language less Pythonic, he just kept building up notes and kept building up what are referred to as Python enhancement proposals until he had an entire second language, which became a Python 3. Python 2 and 3 have kind of commingled now for about 5 years. This, in most communities, would have people jumping to their rafters and saying Python is a dead language. Instead, now the community, originally it wasn't intended for Python 2 to go on in a maintenance cycle this long. However, there's a lot of code invested in Python 2, and they kept adding Python 3 features back into Python 2, and in a few places where Python 3 ideas had kind of compromised performance or compromised usability, they had kind of started to backpedal a little bit on how aggressively they were going to be ditching some of the outdated notions from Python 2. So why use Python at all? Well, if you like a programming paradigm, it's supported. You like object orientation? We've got that. You like functional programming? We've got that. You like design by contract? Oh, we support that too. You like to completely obscure the world of any reference of object orientation, write everything procedurally and punch it in on punch cards? Well, we've got everything except for the punch cards. Most of the functions in Python, that is to say in the core libraries, if you're familiar with C or C++ and have worked on a POSIX compliant, wonderful POSIX compliant platform like Windows NT or any of the Unixes, most of the functions map back from C and C++ into Python pretty easily. It is easy to combine with other languages. There's, at this point, so many different wrapper generators for generating wrappers for C, C++, Fortran, Ada, and yes, Module 3 functions to pull them into Python. I've lost count. The two biggest ones, being, of course, being Swig, and then there is wrappers available through Boost, F2Py, and then there's a number of ways to do it manually through Python C types. It's easy. Part of what brought me into Python was the fact that it's easy to keep code readable and maintainable. If you roll back to the dark era of 2005, imagine a young graduate student who gets faced down with up to 12 undergraduates and told, this is your research lab, these are your research partners, and being a Perl user. Python mandates formatting, it mandates white space, it's part of the syntax of the language. And when you have 12 undergraduates writing Perl, which is free form, and there's about 13 different ways to do everything, you basically wind up throwing your code base away about twice a semester. So Python for me became a survival strategy. The other important thing is the price is right. There's no license management, code is relatively portable. The community actually keeps itself aware of the fact that they have a Windows constituency, that they have an OS X constituency, that they have a Linux constituency. They're even aware of the fact that they've got embedded users, and sometimes they're aware that they've got cross-compiling HPC users. Unfortunately, there's some poor developer who gets stuck on Python dev with most of those tickets. There's also a very low learning curve. Again, if you're used to basically any form of programming, you can set down in Python and in about an afternoon be productively on your way. It also comes with a highly enthusiastic and very helpful community. The community is usually very good about answering questions, answering them in a constructive way. You have not seen quite so many people quite so excited as at PyCon when they begin talking about asynchronicity and coroutines. You would have thought it was a rock concert and the audience was made up of 13-year-olds out for their first night. So just to kind of give a quick example, if we've got two pieces of code, one is in C++-ish, just basically take integers, walk through them, and if they divide by a certain module, print them out and give their powers. Same code next door in Python. Again, relatively simple, relatively short, and do notice that the formatting is very strict. That's one of the biggest hits that people have on Python is that the white space and the formatting are important. The best analogy I've got is it's like having a partner who likes to come home and resort your sock drawer. The first few times that they do it, it's going to drive you crazy. You can never find anything. And then after a while, you just get used to it and you enjoy the obsessive compulsion. So why use Python for scientific computing? Well, because batteries are included. Unlike Lua and some other languages, if you can think of something that's really important, except for, of course, numerics, it's baked into the language. There's also a very rich computing ecosystem, and we'll talk a bit about that more in a minute. The most important reason to me is there's a great balance between computational performance and time investment. One of the general rules is you will spend probably 90% of your time in 10% of the code. That is to say where your numerical kernels, your solvers sit. That is where you're going to spend most of your time, and more often than not, someone has already gone to a lot of trouble to package those nicely, develop wrappers for them. I don't have enough good things to say about NumPy, SciPy, PETC for Pi, the Trilinus wrappers, the Sundials wrappers. Essentially, they've kept me from having to ever stop and think about, am I passing things in and out correctly in C++? They've kept me from hours of banging my head against Boost templates. They basically enabled me to sit down and get very productive work done very, very fast. And in many cases, to do a lot of my development interactively, so that way I can see what's happening within the code, as opposed to write some code, compile, submit a job, go check the oil in the car, dig up a dinosaur, run an application, run a CFD code to see if I can find another oil reservoir, and come back and then repeat that cycle over and over again. Versus when I'm developing with Python, I can usually just work interactively and let the session go and kind of see where my code is bailing out and where the problems are arising. The other important thing is the tools, again, are almost entirely open source and free. There are commercial distributions. I do have great things to say about them. I respect greatly the work done by Continuum Analytics. They have a package called Blaze that one of the other complaints about Python is performance. Well, they've got a layer called Blaze where basically you add a simple decorator to your mathematical functions, and it uses LLVM on the back end to compile it and lets you run those kernels directly from Python on a CUDA-enabled platform or on a native host CPU. That is to say, they're actively compiling Python function by function as opposed to loading some sort of C or C++ or Fortran kernel. There's also commercial support in addition to that provided by Continuum Analytics through a company called Nthought, both of which the people at both are very good. They're very responsive. On the other hand, they tend to focus on the majority platforms out there, so x86 boxes running Linux and or Windows. Not so helpful if you happen to be the proud owner of several 100,000 PowerPC cores. The other very important thing, and one of my favorite stories, is that there's no license management for the modules that keep people productive. John Hunter, who originated one of the most important plotting libraries for Python, Matplotlib, he was a PhD student at the University of Chicago, and he had been using a commercial toolbox that might rhyme with MATLAB. And the University of Chicago MATLAB server kept crashing on him, preventing him from actually being able to finish his dissertation. And so in the time that it took the University of Chicago's ITS to fix their license server problems, John basically sat down and had written the first version of Matplotlib so that way he could get his dissertation done. There are a lot of science tools for Python. The two big ones that always stand out are NumPy and SciPy. At this point, if you're interested in GPU computing and offload engines, there's PyCUDA, PyOpenCL. In the parallel space, there's PETSI for Pi, PyMPI, PyPar, MPI for Pi. For wrapping, you've got Swig, Cython, C-types, F2Py. Again, the list kind of goes on. In the visualization space, there's Matplotlib, Visit, Chaco, Mojave. Essentially, if you can name a tool, it's available. And even if you're stuck using other languages like R or MATLAB, there's actually, at this point, very well-developed interfaces to be able to interact with your existing MATLAB toolboxes and even to be able to swallow up entire MATLAB programs whole. It's a little bit broken now, but at one point, one of the consulting firms had a MATLAB translator whereby you would feed in your MATLAB code and it would spit out, well, I'm not going to call it good Python, but it would spit out Python on the other side. So why don't you want to use Python? It's just, the first thing is there's a really low learning curve. It is easy to fire up the interpreter or open an editor and just throw out your Fortran, your C, your C++, your Ada in Python. This means that a lot of people begin developing code, and as they get used to Python and they begin to understand its features, they look back at their code base and they kind of go, what have we done? At the very end, I'm going to talk about a project that's near and dear to my heart, and I'll reflect a little bit more on that, oh my, what have we done when we get there. The other thing is Python is strict about some forms of formatting, but not others. There's a very important document out there called PEP8, and it's not the law, but generally the stance has always been in the community, if you write your code following the suggestions made in PEP8, your code will almost universally always run. The other thing is because it is so easy to turn out code and turn out code quickly. A lot of people tend to re-implement the same things over and over and over again. If I ever look at another heat transfer problem re-implemented in Python, if I ever look at another Navier-Stokes solver written in Python, if I ever look at another projector augmented wave DFT code written in Python, I possibly will cry. The other reason to avoid it at all costs is it is, again, easy to combine with other languages. And this means that there are reasonably sized communities around most major and important packages. Some of these bindings were written by people who kind of fell into that low learning curve camp and basically just provided their C or their C++ or their Fortran interface into their existing libraries. One of the best examples of Python bindings done right is the PETC for Py bindings and the NumPy for Py bindings, which I'll come back to. I'm not going to call anyone out for the Hall of Shame, on the other hand, but when you get told that you have to pass data into the ctypes module to pass it on to a library, those bindings are a little bit weak. There's other reasons not to use Python. There's constant revision of the Python language itself. There's a process called PEP, or the Python Enhancement Proposal process, whereby people say things like, we really, really need a special function to represent vector multiplication. And so they will literally write up what it takes, what they think the operator should look like, how they believe it should be implemented, how it should address functionality within existing modules, and they will submit it. Other folks will file PEPs along the lines of, I think Python loads too quickly. Therefore, we should rewrite the Python loader to completely and totally use files. And this is the era of cloud machines and diskless computing. The other thing is the language maintainers, more often than not, strive for philosophical consistency. And when I say philosophical consistency, they spend a lot of time thinking about what makes code Pythonic. And when they discover that somehow two ways of doing something have crept into the language, they will viciously and mercilessly stomp out the one that they feel is less Pythonic. Likewise, sometimes they will look at something and go, there's an entire community that has risen up, say, around cross-compiling. And it sucks that these people are spending all this time on cross-compiling and maintaining patch sets and maintaining tool chains. We're going to help them out by pulling elements of what they've been doing into main. And in the process, completely and totally throw everybody who's cross-compiling for embedded work for a loop for the better part of a year as they continue to evolve what they believe should be done within main. The other thing is when they decide that there should be one way of doing things, they will retire those features. They don't tend to truly retire. They tend to go off hiding in corners of the language and or being protested until they come back in. A great example of this was Lambda, which came in when Guido was kind of on a functional programming kick and disappeared almost as quickly. And then it was back again, mostly because people had spent a lot of time writing code that used Lambda, and a lot of things they had figured out work better or easier to read with Lambdas. But it was gone long enough for generator functions and list comprehensions to kind of win hearts and minds, which is kind of what they had wanted. There's a famous statement built into the Python interpreter. If you do import this, you'll actually get a poem, and a subsequent from it is, in the face of ambiguity, refuse the temptation to guess. There should be one, and preferably only one way to do it, although that way may not be obvious at first unless you're Dutch. I get a reference to Guido. Now is better than never, although never is often better than right now. That's to say, you will put in a PEP saying that it would be better to have a function fuse multiply add or some sort of vector multiplier, and it will sit there for 7 years. I have great hopes, by the way, that Python loading will be fixed by the time I retire. The other big thing that tends to pop up is the principle of least surprise. That is to say, to keep the learning curve low and keep the language accessible. When they find things that people find off-putting or surprising, they try to phase them out of the language. A side effect of this, and a major early selling point for Python for scientific users, was the fact that everything was strictly IEEE 754 compatible floating type. This, of course, throws off our friends in the web community who get upset when they divide, say, 1 by 3, and they don't get 0.33333333. Instead, they get, you know, not a number or an int or something that is not what they would expect using a desktop calculator. And so they wound up winning in Python 3 and switched the default decimal representation from IEEE representations to decimal representations. This, of course, threw off a lot of science users, and the interim compromise was, we'll let you do both. So again, why not use the CPython interpreter? It's inefficient. The Python 2 series is actually a true interpreter. It is walking your code line by line by line by line by line. This is part of the reason that became so important for so many projects early on to be able to jump into another language and to write their kernels in something more compact and more efficient. Complaints about performance have actually often earned the response on list and very publicly from various people that you should try go doing X, where X is using Python, using NumPy, or Guido famously stated if you have your bottlenecks truly are in Python, try go using PyPy, which is, again, Python with a JIT backend. Python 3, life gets a little bit better because there's the ability to actually hijack the internals of the language. And so the revised internalized parser has the ability to actually look ahead and say, oh, this is a loop, or this is a matrix multiplication, or this is some form of data structure. I can simplify this, or I can reorder this for faster execution. On the other hand, it turns out that Python 3 currently is still running slightly slower than Python 2 is for many of the same functions, but a lot of that is spent in overhead. Python 3.5 should be out within the next month, and actually speed-wise, it's pretty much back to where Python 2.7 was several years ago. One of the favorite things, if you get a bunch of Python programmers talking about threads in a room, is you'll hear GIL complained about, and you'll hear GIL complained about a lot. And what the GIL is the global interpreter lock. So early on, in order to keep CPython easy to interface and easy to develop, they decided that there would be that they would support threads, but then they would have a giant lock around all of the interpreter's memory, such that only one thread at a time could access the interpreter's memory space. This, of course, creates certain problems if you're writing multi-threaded code, or if you're trying to say, do I/O in large amounts, write a web server that's highly threaded, and basically it winds up grinding everything to a halt. Through the years, they've made improvements to the GIL such that you can do things like I/O and other threads. They added an entire module called multiprocessing that works by forking the interpreter so that you have multiple interpreters, each with its own GIL. But they still have not removed the GIL from Python 2 or Python 3. David Beasley, who is kind of an esteemed member of the Python community, many moons ago of Lawrence Livermore, who famously wrote the first Python MPI interface and only implemented all reduce because that was the sole function he needed for his doctoral thesis, actually gives a really great talk about everything you ever wanted to know about the GIL and why it sucks and why it will continue to suck and why it's not going to ever go away, at least in CPython. Other things that really kind of will make you want to run away from CPython, distutils. Distutils are baked into the Python language. They're common. It is a de facto way for packaging Python modules for easy installation. What winds up happening instead is if you're trying to do something that, say, where you need to use GCC but link in, say, Intel's math kernel library or a particular version of NVIDIA's CUDA BLAS, you will spend hours and hours and hours screaming and cursing and wondering why it is that distutils will continue to pull the unoptimized operating distribution provided copy of Atlas out of user lib. It is possibly the single most frustrating thing there is about actually doing work with Python in an HPC environment is building things for an HPC environment. Other things that tend to turn up and be trouble, the fact that you get lots of small file I/O as part of your runs. The other big problem is occasionally you'll get people will want to know, where did this crash within my mixed language code, or where is my actual bottleneck, or where's my slowdown? And a lot of tools do not play nicely, ranging from debuggers to performance tools. I may be getting some dark looks from one particular table, but they do not like, most of the tools do not like it when you mix languages. A lot of the easier to use performance analysis tools rely on, particularly for HPC, rely on NumPy init and NumPy exit, which don't play particularly well with shared library support, which most Python interpreters are built with by default. So in short, all the tools that you count on to figure things out when they're really, really broken and where they're going really, really slow are just not going to work. So again, at this point, I strongly recommend using Ada, using something else. It's actually not that bad. There's ways around it, but they take a lot of time and investment. I have space for a quick demo, but we're actually going to walk through the parts that lead up to the quick demo, mostly because anytime I've ever given a live demo, Mira goes down. And I'm going to wait until all the admins have gone home for the day before taking Mira out. So one of the most important packages out there, and quite possibly the most important Python package for everyone in this room, is NumPy. It provides you n-dimensional homogeneous arrays. They can look like C arrays. They can look like Fortran arrays in memory. You can view them view them in various ways. They're kind of like the Latin of the Python numerics world. Just about every Python package out there with for science will wind up interfacing and dealing with NumPy arrays in some form. They provide us a set of universal functions, basic math, linear algebra, FFTs, portable random number generators. NumPy gives us very simple data file I/O, text, raw binary, native binary forms. There's much better ways like H5Py for doing HDF5. There's netcdf bindings, which are separate, but they're definitely there. It provides out of the box the tools for integrating with C, C++, and Fortran. And more importantly, those mathematical functions that are available to you in NumPy, usually their heavy lifting comes out of Atlas or MKL or OomphPack or ScalaPack or FFTW, so on and so forth. So that way you get an easy to use interface that's actually relatively well documented, but you get the high performance of whatever libraries were behind the scenes. Creating NumPy arrays is relatively simple. Just import, one of the common pieces of syntax is import a module as something shorter. If I cannot drive anything home, whatever you do in life, you can run over the neighbor's dog in front of their kids. You can turn in tape, this doesn't make any sense anymore, but you can turn in your tapes not rewound. You can keep library books out. You can sleep through your advisor's class. But whatever you do, do not do from package import star. All other transgressions in life are forgiven. Mostly because it pollutes namespaces, it makes life harder to debug, and 5 years from now, when you're trying to refactor that matrix diagonalization, and you're trying to figure out exactly where something is coming from, it makes it much, much, much harder to figure out where it came from. NumPy arrays are easy to declare. It's easy to declare a linear array of things that are evenly spaced for people who like series. It's easy enough to fill a matrix. All these are 2D, but it's easy to create 3D, 4D, 5D arrays. Fill them with zeros. You can approach them like you would approach any Python list. They use similar slicing syntax and ordering syntax. It is worth noting that you're actually slicing through Python arrays, that almost everything is a pointer. It is not an actual copy or a deep copy. This catches a lot of people who are new to Python off guard, particularly because Python really, really likes it when things are pointers underneath. At the same time, there are things that a lot of people coming out of C, and C++ think should be easily updated, but are actually immutable. Things like tuples, strings, numerical values. And so when they get something that looks in a debugger like as a pointer, but then the contents don't get updated, they get really, really frustrated. So it's one of those things where you should actually, if you begin developing in Python, keep in mind as to which types are immutable and which types are not. And so that most things that will be pointers, unless you do an explicit deep copy. 95% of the world doesn't need to worry about that. For the 5% who do, they will realize it after days and days and days of debugging. Again, the universal functions. So we declare a NumPy array. We decide that, let's add 1 to each element in the array. So we do a+1, and instantly we get a broadcast where it's just been added to all elements of the array. The newer versions of NumPy, again, most of this is done underneath the sheets in C and Fortran, so it's relatively fast. There's one other big package that's pretty common, CPy, which is extensions that contain things like solvers for optimization, additional linear algebra routines, integration, interpolation, FFTs, signal and image processing routines, ordinary differential equation solvers. And again, just like NumPy, which it sits on top of, all the heavy lifting is done in C and Fortran. Almost every workstation that you sit down on that has Python installed probably has NumPy and maybe has CPy installed. Some pieces of CPy are not as well maintained as NumPy is in general, but overall support is relatively good. To bring this towards HPC, of course, we have NPI for Py, which is my favorite set of bindings for Python. It wraps whatever your native NPI is. It provides all the NPI 2 and now a lot of NPI 3 features. It's very well maintained. Lissandro Dawson is incredibly responsive to bugs. He takes a lot of suggestions very well. It's one of the most Pythonic interfaces to something that is typically unPythonic available. It's insanely portable and scalable. The NPI for Pi came onto the Blue Gene L, I know 8 years ago, and it installed, it ran, it worked, it calculated pi, met scale, and everything was beautiful. I've never been so flabbergasted that something worked quite so easily. NPI for Pi jobs must be launched by NPI run or NPI exec. This kind of puts a damper on things being interactive, even though NPI for Pi for people doing workstation development does have an interactive shell. Each link launches its own independent Python interpreter. This becomes important in some cases because you'll sit there and go, I have launched 64 of these on a Blue Gene Q compute node, and then you'll spend your time wondering where your memory went. Well, now you know. Each interpreter only has access to the files and libraries that are available to it unless distributed by links or if they're available through a parallel file system. This catches some of my non-HPC-minded colleagues off guard, because they will launch 1,000 they'll launch 100 instances out on Amazon's EC2, and then be stumped as to why 99 of their ranks crashed when they weren't able to read files. Any communication is handled by the underlying NPI layer. So NPI for Pi will not fix that busted all reduce. It will not fix broadcast inefficiencies. It will not solve issues with all-to-all V. However, on the other hand, it'll be such a pretty interface that you won't care. It will and can ship any serializable object. That does not mean it can reduce any serializable object. So just because you have an NPI reduction function doesn't mean that it'll necessarily work. I had students trying to do text language processing using NPI for Pi, and they kept being stumped by why they had one huge string as output at the end when they were doing sums. Well, Python looked at it and goes, I know what this is. This is a string. I'm going to just concatenate. It did not cast. Just about everything, with the exception of strings and integers, are pickled. That is to say, it uses Python's built-in serialization. Python pickles are relatively common. And again, most Python modules that deal with pickles handle them pretty well. NPI data types, on the other hand, integers, floats, doubles, NumPy arrays, buffers are sent without pickling. They move about the same speed as they would in C or C++. And for the most part, the best way to tell things apart is to see if the method is capitalized or uncapitalized. And I always, again, have this conversation with students and people who aren't used to scientific programming, where that when in doubt, if it's a memory buffer, that is to say something that would come out of C, C++, Fortran, or a compiled language, it'll probably be sent as an NPI data type. If it's a giant collection of pointers that will require a deep copy and translation in and out of some sort of object format, it's probably going to be pickled. So we've got two simple codes, just calculating pi with NPI for pi. So at the top we have an import statement of a different form. From NPI for pi, import NPI, and that's just pulling out the one member of that module and importing the built-in random function. We declare NPI com world. You'll notice that there's no NPI init or NPI finalize. All of that's taken care of for us by the NPI for pi module. We find out what our rank is. We get the size of the system. We declare a number of samples, and then each rank for its collection of samples generates random x and y, sees if it falls within inside of a circle. If it does, it ups the counter. It does a local calculation for what its value of pi is, and then there's a reduction function to bring it all back to rank 0, and then only rank 0 prints it out. It's basically the same pi function that you would write in any other languages. This, of course, is going to have a decent amount of overhead, mostly because in that range statement, it's going to build at a very, very, very large Python list, which is not necessarily the most memory compact structure nor the fastest. It is going to then wind up calling through Python's random function, which is usually sitting on top of your local libc's random function, and again, responsible with all the same tolerances and intolerances of that, generating 2 values, and then using the interpreters built in to do a quick calculation and move on. Or you can actually rewrite to use NumPy. It's a lot more compact. Everything is going to wind up being C buffers, and everything's going to move relatively quickly. So, and really using NumPy and using other people's solvers, people who've put a lot of time into it, using their solvers and their method is really the best key there is to getting decent performance out of Python. One of the big questions is, does anybody actually do this stuff in production? And the answer comes back, yes. There's GPAW, a massively parallel Python and C code for electronic structure calculations. It is a projector augmented wave code, a form of DFT. It is almost entirely written in Python and C using NumPy throughout. It is fully open source. It has, at this point, probably 100 or so contributors scattered across 3 continents. To kind of give you an idea of the evolution of GPAW, it started off as maybe about 20,000 lines of Python, and now it's well over 100,000 lines of Python with increasing amounts of documentation, increasing amounts of test. You'll notice that the amount of C code is stayed about constant because, again, that's kind of where our solvers are hiding. And libxc we won't talk about, but we've managed to make it go away. It makes us feel much, much better. When it comes time for execution, we spend probably about 10% of our time in Python and 90% of our time in C. That performance engineer who wanted to stop Python users, well, kind of my rebuttal to him is, well, it doesn't matter. Everybody else is just wrapping dgem out of BLOS anyway. We're doing the same thing. It just happens that we spend very little time in development cycles developing the remaining 90% of the code. Are people actually doing science with it? Yes. We have a a lot of people look at that slide for the first time and they ask if that's our strong scaling numbers, and instead it's actually our publication counts as things go on. So I'd say yes, there is a very strong user background. Nick Romero, who's kind of my internal mentor, arrived at ALCF, kind of got assigned GPAW because that was what one of our Insight projects was using. And at that moment, he had never touched Python before. His programming background was in Fortran 77, and within a year, basically wound up being a relatively major contributor. Our strong scaling results are kind of cool. We can keep going up in core count. There's actually an internal refactorization underway, which is causing some headaches, but we expect to be able to use almost all the threads and all the cores on Mira, provided that we've got a system that can match. On the Cree XT5, again, we're pretty close, strong scaling wise, to ideal. Not a lot of the other codes can say that. For the most part, we can get 10 to 15% of peak core performance, which doesn't sound great, but actually, for most codes in production, that's relatively impressive. There are a couple bottlenecks just algorithmically that come out of PAW that involve the duplication of memory. There's a few other places where we could have much better solvers, and those works are in progress. One of the things that kind of frustrated us a lot is the fact that when you get on these super high-performance computing systems, that they've got special lightweight kernels. They're missing a lot of features, dynamic libraries, missing system calls. In BlueJean's case, all I/O was forwarded. Python relies heavily on dynamic loading. This means that we spend a lot of time trying to figure out if we could build everything into one binary executable. That proved to be really painful and really slowed down development. We tried a modification of CPython to actually reduce the number of things loaded. We actually, at one point, put time into hacking apart glibc so that glibc's dynamic library loading would occur in parallel along with most I/O functions. If you would ever like to take on an unmaintainable project, try hacking apart glibc and pieces of your operating system's kernel to make them parallel where they are normally serial. To give you kind of an idea, every time you import a module in Python, you wind up with a lot of metadata traffic. You get a lot of you wind up walking all the directories in your Python path. You wind up opening and closing, trying to open and close files that may not be there. It'll try to compile down to bytecode all the uncompiled plain text Python files that it finds. It is actually incredibly severe. By default, on 8 racks of the BlueJean P, they had startup time of 45 minutes. Trying to go up to 32 racks on the BlueJean P, again, it was one of those situations where you went out back and you started to write a reservoir solver while you were waiting for Python just to load. To kind of give you an idea about where things are going, we're going on that front. That is the time loading processor core-wise. I want to say that one came off of the BlueJean with standard Python versus what it took when we finally hacked in a parallel import underneath. All of this, of course, for Python 2 wasn't that difficult because more of the internals were in C. As Python 3 has kind of become coming out into its own, they wrote more of Python in Python, and so we're banging our heads against the loader now. Do we have any questions? Yes. Show me the back.
I'm wondering what is the real impact of having an extremely broad and how to put it mildly, extremely varied community in terms of code quality.
So what is the impact of having an extremely varied community on code quality? It's actually I think overall it's been a positive impact, mostly because you get a lot of eyes looking at algorithms and looking at issues in ways that one community wouldn't. While I kind of pick on the web community about their fancy decimal math, on the other hand, they've made a lot of strides into improving concurrency. They've made a lot of strides in improving internationalization and Unicode handling. That community is also one of the communities that strongly pushes security and testing, and I think they've overall made a major improvement. Likewise, I think a lot of the folks coming out of the embedded community keep Python main aware of its memory usage. We keep them very, very, very aware of things that will not run well in a low memory or a low disk environment. So in many ways, I think that varied community is a very strong strength. Yes, sir.
I was just generally curious on your opinion comparing R as a statistical programming language with Python. Where do you see the pros and cons, or are you just completely sold on Python and R is just kind of an aberration, or kind of just on that particular aspect, statistical programming?
So with statistical programming between R and Python, it kind of depends on what you're doing. The R community has a lot of really strong internal development. They've got a lot of really good documentation. In some ways, I feel that R, though, is a little bit limited. Most of its users are people coming from a statistics and analytic background. And so sometimes when it comes time to interface R with, say, something like a piece of laboratory equipment or a web server, or to interface it with some of the other scientific libraries, those projects tend to take a lot longer and have a lot more overhead, versus Python kind of comes with batteries included. One of the bigger and more impressive packages that's popped up over the last couple of years is called Pandas, by a guy, and I'm going to murder his last name, which is about to be embarrassing, but I want to say Wes Kenny. He also just published a Python for Python data analytics book, which is really quite good, that addresses some of Python's initial shortcomings in that space. Personally, for the things that I feel more comfortable doing with R, I will use R Python and get kind of the best of both worlds. For other spaces, I find that because the statistical analysis and data analysis community is big within the Python community, I find that as people see things in R that they really like, they tend to get sucked in.
There's a new scripting language called Julia, and it's very. They are saying it's much faster than Python. So, what's the reason for Python to be slow compared to Julia?
So, what's the reason for Python to be slow compared to Julia? Well, the biggest problem with any sort of speed comparison is you always have to define slow. There's Python in general, again, means CPython. So there's things that the CPython interpreter just doesn't do, like loop optimization, looking ahead, and in those places it falls behind. Julia, on the other hand, sits on top of the LLVM backend and LLVM's JIT. So it does a lot of internal JIT optimization at execution time. Those are things that are being addressed within the Python community through projects like PyPy, being addressed through Continuum Analytics and Blaze. So I kind of, to a certain degree, I feel that the speed is a non-issue. One of the places where I think I feel limited when I use Julia is my ability to bring things in from the outside. And I think that will continue to be one of Python's strengths. The other thing that I find interesting in terms of speed comparisons is the ability to actually sit down and develop. Python's development tools, I think, have come a long way, a lot faster than Julia's have. Python's also had maybe now a 20-year head start in that space. It'll be interesting to see how the LLVM ecosystem develops and how much of that Julia manages to take advantage of, particularly with regards to debuggers and performance analysis.